Thank you so much. It's a great pleasure to be here. This is the first time for me to ICTS, although I was in Bangalore for 5 years and then kept visiting. It's actually it's an honor to be here because both these Krishnamurti and Chandan Dasgupta are my teachers, and whatever I learned and whatever good I talk about, I owe it to them, and whatever mistakes I made are mine. So there's a famous Bengali novel in which this is written by the father of this famous Indian film director Satyajit Ray. His father's name was Sukumar Ray. So there's a novel which is somewhat an absurd novel in which the protagonist says that we start counting backwards after 40. So on that count, both Krish and Chandan are around 15 now. So I hope to be around for the next 65th celebration, and it's a pleasure to be here. I just hope they carry on. What I will do today is introduce you to this subject of interfaces, which has got a lot of attention of late. The discovery came in 2004, and then it hibernated for about 10 years, owing primarily to the difficulties in making samples. But then when the people started making samples, there is a plethora of papers that came out. And so I'm told in the first 2 years, 73 papers came out in Nature, Science, and PRL. So this is almost like a record. It's like high TC. So the idea was, so I will base my talk on these, will not talk about the starred papers, which is Avik Bid I have collaborated with, who is one of the organizers and he's an experimentalist. So I will talk about the others if time permits, but my main intention is to introduce this subject. So, so these are interfaces with this kind of a structure. On two sides, you will have ALO2, for example, and TiO2. Now, these are two good band insulators, LaAlO3, and with a band gap of 5.6 electron volt, non-magnetic. Then there is SrTiO3, a very well-known substrate. It's also a band insulator. Band gap is about 3 eV, and it's also non-magnetic. So you put them together, it turns out the interface becomes metallic. So it's a metallic interface out of two band insulators. So the idea is that the whole notion here is that you are trying to replace the well-known semiconductors, which have served us as electronic materials for so many years, by oxide interfaces if possible. But this is an odd exchange because semiconductors, they have brawn but no brain, and I hope there is no electronics person here. And they are excellent materials with very good material properties, with good control over the materials, but there's no exciting physics. And then there is this correlated oxides. They're intelligent but wayward in that they're not controllable, very poor materials, which is what all intelligent people probably are. So the idea is that you can have a marriage of semiconducting oxides. So a marriage in heaven or hell is the question. And this is the classic conundrum that whether you generate a super offspring, there's always a 50-50 chance. This is this famous, as Andrew Millis puts it, this is famous George Bernard Shaw, Isadore Duncan dilemma. So the idea started in 2004 with this Nature paper by Harold Wang and his collaborator at Bell Labs, and they showed that these two, when put together with sufficiently good material properties, there is an interface which is metallic. How thick the this interface is a debatable question, still not answered, but this is certainly not more than a few lattice spacings thick. The whole, another interesting thing they observed is that the better you make the sample, the worse it gets as a metal. So it's just the opposite of what you normally see. So it's sometimes called annealing, insulating state by annealing. So normally you expect annealing produces metallic state. Here it's just the opposite. You anneal with higher oxygen partial pressure, make better and better samples, you get less and less good metal. So I come from an Indian Institute of Technology, so I will have to show some technology, and this is the paper which actually shows the first technological application of this material. Okay, so this is the way they do the experiments. It's mostly done through backgating, and partly because this SRTiO3 has a much better material property, and it's easier to backgate here. So in some experiments, they do the experiment from the top, but in many other experiments, like Manhart's, this group, they actually bore holes and take contacts all the way down to the interface. So there are controversies regarding these measurement techniques, but still, these are the major ways one does the experiment. The surprise came in a paper in 2008 when they put less than 3 LAALO3. So SRTiO3 is here. Then you start putting layers of LAALO3, and then you just plot the conductivity as a function of the number of layers, and you see that before you go to 4, there is no metallic conduction here at the interface. So 4 is a magic number at which the conductivity shoots up and becomes a metal. So this is another paper with the same data, almost the same data, but this just shows this extraordinary phenomenon that you have to have more than 3 layers. It turns out that if you go beyond 8, it starts degrading, but it takes a long time to make it. I don't think anybody has found insulating by increasing the number of layers. Okay, so this is the crystal structure. So the crystal structure has a cubic phase. The cubic phase is as you can see here. So it's AO and BO2 combined, they form the perovskite. And so if you view along the 001 axis, there are 2 layers. One is this AO and other is the BO2. So AO plane has charge Q sub A minus 2, and because oxygen has minus 2, and BO2 plane has Q sub B minus 4. So you have to put them equal to make a charge balance. Now there are many ways one does it. So one is Q sub A equal to 2, which gives all the sheet charges. Sheets have no charge in this configuration. So these are non-planar layers. But there is this other choice, which is the one I'm discussing now, which is LA, where you have Q sub A is 3, which makes these sheet charges plus and minus 1. So these are called polar layers, and this is the situation that I'm going to describe now. So this is the charge configuration. You have minus 1, plus 1, minus 1, plus 1 alternating. So a simple back of the envelope calculation gives you an electric field profile like this. And then of course you have this potential, which is you have to add this V sub n minus 1 at every layer, and then just immediately starts diverging. So this is the catastrophe that people talk about, that there is a huge potential that builds up inside the system if you allow it to remain polar. So there is a solution for that, and I'll come to the solution. So the other thing to note here is that the electric fields inside are volts per angstrom, which is exceedingly large, if you allow this to continue. Okay, so the way turns out nature solves it, or the system solves it. One of the suggestions is that there is a plus charge 0.5, minus charge 0.5 develops at the 2 ends. So then the electric charge profile is this, field profile is this, and then it just controls the potential. So it's like a capacitor where you have put plus and minus charge at the 2 ends to balance this huge potential that builds up. So this is a cartoon for that. So you transfer charges and then make this. There are many ways you can do it. There are lots of constructions people have gone through, and so these are electron doped ones, these are hole doped ones. I mean, it depends on which termination you are using. You can have holes or electrons as your carriers. So for both of them, there are mechanisms by which you can transfer this half charge from the top to this to the bottom of this, to just below this interface. This is another paper where actually they showed something interesting. Again, Manhart, I believe. Yeah. So what they showed is that you not only is this oxygen, I mean, poor oxygen partial pressure important. It could be important, but what is more important, according to them, is the LA versus AL ratio. So what they say is that if you have a LA-rich system, then you are in trouble. So I'll come back to it, and these are the vacancies they created, and then they showed how in presence of such vacancies also you can have you can manage this polar catastrophe. So as I said in the beginning that if you lower oxygen vacancies, make better samples, I mean this is one of the reasons where the PLD samples do better. So this is an example again as how the conductivity drops as you increase the partial pressure of oxygen. This is Manhart's another interesting paper. So this is what I was referring to, that this ratio turns out to be very crucial. So there is a lot of talk about these vacancies because it turns out these vacancies are necessary. At least some people believe very strongly that these vacancies are the ones which produces these carriers, extra carriers. The intrinsic carriers are mostly localized. So the idea is that these vacancies will give you free carriers, and they are the ones which conduct. But this paper at least suggests that there is, you really do not know these vacancies. They are not necessary. They may be there, but what you need is this ratio between LA versus AL. So there is again almost a magic ratio of 0.97. So your stoichiometry has to be poorer than that to produce for you a good metal. So it always works counter. You have to have poor stoichiometry to give you a good metal again. So PLD samples are mostly here, and that's why they do so much better. So the first emergence was metallicity out of two insulators. Then appeared the second emergence, which is the superconducting interface between two insulating oxides. So this experiment by Rarian and company showed that at around 200 millikelvin, you can actually have a superconducting transition. This transition is fairly sharp. And then it has a very, very small magnetic field required. The critical magnetic field required is exceedingly small for you to destroy superconductivity. The other interesting thing is that 8 UC of LaAlO3 seems to be the best combination for superconductivity. That has the highest superconducting transition. What this superconductivity is, I'll come back to later. So this is a study with respect to gate voltage, and one can show in the next one, here, you can see that by changing gate voltage, you can actually go from the superconducting state to the insulating state. So there is a superconductor insulator critical point here, where you actually this number R sub Q is almost like H by 4 E square, which is like 2E bosons resistivity, almost close. So the features of superconductivity is that people believe this is longitudinal optical phonon mediated. There is a very low carrier, sorry, this is plus 13, low carrier density, and TC shows BKT behavior, I'll come to it. 2 delta by KB T sub G, T sub G is the gap closing temperature. So that at the temperature at which the gap closes, it's about 3.4. So it coexists with ferromagnetism, which I'll come next. It's fairly good moments. Superconductivity is actually enhanced by magnetic fields. This is another puzzling feature. The magnetic field assisted transient superconductivity leading to a possible hidden order has been seen by Avik and company here in Bangalore. So what they found is that you can have a time-dependent magnetic field. If you put it on this sample, then TC appears to rise with it at a certain ramping speed, and at a certain value of the magnetic field, when it is ramped down, the superconductivity appears at a higher field, at a higher TC, fairly higher TC. TC and TG, you can calculate from here. It's so this is about 3.4, and corresponding the gap, if you measure the gap in terms of temperature, that will give you a ratio which is much less than this, much more than this. So that is much less. Good question. TC is measured. Okay, so this is the one. So they mostly do resistive transitions. So so this is superconducting phase diagram by Caviglia and company. So what they do several things. They find the superconductivity as a function of gate voltage. They identify a quantum critical point here, and then they fit this line with this kind of a formula which comes from BKT, and they find that this Z nu bar exponent is 2/3, which is very, very close to what you expect from a BKT transition. There is a paper by Behania and company where they actually compare the SR-TiO3 superconductivity doped SR-TiO3, which also has very, very few carriers, with this one. So they find that, so this is the phase diagram corresponding to that. Interface belongs somewhere here, whereas the one which is SR-TiO3 has two domes, one here, another here. This is the one I will concentrate on. So there is also a change in slope at this point where it hits the superconducting transition temperature. So this is another example. So this one, they fit to this kind of an exponent, which is where you again calculate this exponent and it turns out to be half. They find a very good match with this. So they have done several things, and almost all of them lead to a BKT kind of scenario. So this is the gap as a function of both gate voltage and temperature. So this is the gap closing temperature, as you can see. It's about again 200 millikelvin to 500 millikelvin. Depends on the gate voltage very strongly. So these people actually compare everything in high TC nowadays. So this is a comparison which is done here. So T gap, you can see now. Subrata, you can see how T gap and TC behave. Then came the third emergence, which is magnetism, and this was as late as 2011, and people found a ferromagnetic landscape in this interface, and so the corresponding superconducting interface is, can you just, so the superconducting profile is this. So this was done with scanning squid susceptometry, magnetometry here and susceptometry here. So they plotted superfluid density along with the magnetization density. So they find there is a ferromagnetic order which is very weak, is very soft. You can actually touch this scanning squid head and carry this, you can just take this along with this head. So you can move it along on the surface. So, okay, so this is also expected. There is a strong planar behavior of the moments. Moments are aligned in the XY plane, perpendicular to 0, 0, 1. There is a strong anisotropy, and so as you see, this is the counts. It's at 0 is the angle with the vertical. This is XMCD, which confirms again that this is the theta angle. As a function of theta, you can see that the moments are almost all along the 0 degree. Let me skip this. This is the one I was talking about. that there are two ways one does this contact and non-contact. If you make contact by your squid, then you can actually carry these moments along with you. So they can be just taken along. You can move them along with your tip. So they are very soft, but there is about 0.4 mu b per unit cell moment in this system. So fairly, it's not bad. And this is again this contact measurement. So you can create this square. You just leave this. This is in contact, and then leave it. Then you see that the magnetic regions, patches are all residing within this square. Let me skip. There is a paper by, I think inspired by Bhaskar and to some extent, that there is a strong possibility that these systems are actually phase separated. So the issues at a glance are the quasi-2D electron gas at the interface, which more or less people believe they understand, if you believe in polar catastrophe scenario. Then there is this superconductivity. Where does it come from? And how does it look like? What is it? What is its order parameter? What is its symmetry and all that? Then ferromagnetic order, it's a fairly high Tc, 200 Kelvin from two non-magnetic oxides. Then there is this coexistence of superconductivity and ferromagnetism. And then, of course, this extreme tunability with respect to conductor-insulator transition. Then all these issues are being debated. None of these issues are sorted out except for probably this one, polar catastrophe. There are these questions of Majorana bound states which we actually raised, that there are possibilities here. Nature of superconductivity, then hidden superconductivity as Ovik showed. Of course, there is this particular question that I will address also, where people find the oxygen vacancies in order. So D.D. Sharma and company, for example, they have been spending some time on it. This is something that Ovik has done. From resistive noise, he has pinned down the BKT transition. Then there is a new issue that one of the ex-students from here, Arjun Joshua, his group, he and his collaborators from Israel have showed that there is a Lifshitz transition which is expected, but they have sort of found it. They could narrow down the region where this happens. And there are consequences of this which we have worked out now. And then there is a new issue that has come up, that the magneto-resistance, like in high Tc superconductivity, changes sign with gate voltage. Okay, so this is where the theory starts. This is a very simple band structure. It's two-dimensional. Only one band is two-dimensional. In the T2G sector, you have to put one electron there. So dxy is the one where you put the electron in. So that's what band structure also suggests, that there is a dxy band which is very small weight at the Fermi level. So this is the one. This is where almost at least if you don't dope it, this is where almost all actions take place. This is the only 2D dispersing band. Others are all one-dimensional. This one. Okay, I will not get into this. I don't have much time. So there are interesting Fermi surface maps people have found out. Some bands are missing, but that is a different matter. So this is the Hamiltonian we start from. If you are working with the completely undoped sample, then one band probably is a good model. This was first written down by Patrick Lee, and it worked more or less in the initial stages. So we started with this model. What we in addition did was that we put in disorder also, but I'll come back to it. So if you don't have disorder, this is how it looks like. So if your energy bands are trivial, straightforward, the only thing is that since there is a strong Rashba spin orbit coupling, there's an inversion symmetry breaking, so your band will get split. There is a difference here, the gamma points don't match, and the momentum and spin are locked in. So the Fermi surface looks like this, which was originally a square kind of Fermi surface, now becomes two Fermi sheets. So these are these lines. This one is open, so that's the one. So One, we wanted to study what electron pairing, how electron pairing takes place in such a model, and then we have to look at, of necessity, you have to look at finite momentum pairing, because these two are separated by a finite momentum. Now, so that's actually the suggestion that came from Patrick Lee, that there is a finite momentum pairing, and the magnetism and superconductivity survive together, coexist, because of there is a FF-LO kind of state. So that was Patrick Lee's contention in the beginning, and I mean, since he hasn't written any other paper, maybe that is his contention still. But what we did is that we took it up, and then we also put disorder in the system, which is there, you cannot avoid it because the oxygen disorder is, oxygen vacancies are there. So we put in disorder and we did the standard Bogoliubov-de Gennes kind of calculations. So this is what we get. Suppose you suppress you don't show magnetization. This is how superconductivity looks like. Superconductivity appears in patches, which is usually what happens in a disordered superconductor. A lot of people have done this before us in the context of superconductivity. And if you now suppress superconductivity and look at the ferromagnetic patches, then what you find is that there are, with some disorder, ferromagnetism appears with patches, and then you overlap these two, superpose them, and what you find is that where there is no superconductivity, there is no magnetism. Where there is no magnetism, there is superconductivity. So it's a simple case of phase separation, nothing much. Where you don't have superconductivity, magnetism appears. Where you have superconductivity, magnetism is not there. So it has nothing to do with probably FF-LO kind of state. It is just a simple phase separation. Then you can actually calculate all these things and how. So this is like the BCS when you have no disorder, but then as you put in disorder, the piling takes place towards lower delta, and at some point it will hit 0. Yes, we checked that. But that's the first thing we checked actually. So then you do correlation functions. You can see that both of them are somewhat robust with respect to disorder, but that's already seen. A better thing to look at is the superfluid density. And superfluid density, as you can see, goes all the way up to a large disorder. It will not vanish. Then you also see that there are these mid-gap states that appear, there are pseudo gaps that appear instead of full gaps. These are all seen in experiments, and these are expected in a disordered system. So the referee made us do the finite temperature calculation. Yes. That's correct. Microns order. Micron size, yeah. It could be, but it's the nature of the theory, right? If I put in, I would say that in a real system, if you have long range interactions, the patches will be even smaller. So these kind of theories will not give you a reliable size of these patches. Then you have to go and make more approximations, create the domains and see. I mean, that is classically you can do it using classical theory. But I'm saying the microscopic theory at least predicts that there is a phase separation. There is one intriguing phenomenon that people had reported, is that initially as temperature rises, they found that the magnetism rises. Magnetization rises, but what we find is there is no mystery in this. What is happening is that the superconductivity falls faster, so the patches that are free for magnetism to grow are much more. So the average magnetization that you pick up actually rises. And then of course when superconductivity goes down, it falls. Okay, so this is again Pickett's Pickett's calculation on oxygen vacancies, which is the next issue I'm coming to. So they found that if you put oxygen vacancies in, some of the states get into the Fermi level, and the vacancies can produce some electrons that go to the Fermi level. So then we actually looked at what happens in presence of vacancies. We did a Monte-Carlo calculation, and particularly we were bothered by the issue that people reported vacancy ordering, and vacancies form patches. But then what we found is that, so each of these vacancies, for example, has a charge of -2. So given that, then you just do the calculation, and what you find is that at sufficient disorder, there are really these vacancies that form. The vacancies actually pin the disorder pins the vacancies, these oxygen vacancies, and they sort of cluster around. And this is simple energetics that gives you that. Just skip it. Now we have not published this data, so I will not report the data, but I'm just telling you the problem. This is the pristine sample, and what Andy Millis and company have done is that they have replaced this M and M prime by a series of combinations. Now you get about 90 combinations, out of which they took about 21 and did a very large calculation to see what happens if you have anti-side disorder. So what they are looking at is if you just replace this pristine structure by an anti-side disordered system. And they took two different supercells. It's a DFT calculation, so they took two kinds of supercells. One is 2 by 2 by 2, another is root 2 by root 2 by 8. Another they took is root 2 by root 2 by 2, which is the one they finally report. And so then they went ahead and did a DFT calculation. And what they find is that anti-side disorder is favorable in certain cases, and they actually tabulated all the cases where anti-side disorder is favored. So this is their tabulation, one of their tables. So these color codes are basically energetics. The bluer you are, the more blue you are, the better the state is. Better the anti-side disorder stabilizes that kind of combination. So for example, V and Ti, Fe and Ti for example, this interface will be stabilized by anti-side disorder. Whereas chromium and nickel will not be stabilized so much by the anti-side disorder. But they are still stabilized, and this is the unit cell they are using. So now what we have done is that we have actually done this calculation, but now we have put an oxygen vacancy, which they did not. So we have taken all these 21 interfaces, and we put oxygen vacancies, and because we want to put in oxygen vacancies, we have actually enlarged the unit cell, and you put the vacancy, number of vacancies can be that you can go to 25% and 50%. So what we see is that once you put in oxygen vacancies, this whole phase diagram is not stable. I mean, this is not what is going to happen. Such general behaviors are not expected, and we are going to report it soon. The other interesting thing is that there is a magnetism at the back of the whole thing, and depending on which magnetic structure you have taken as your ground state, this phase diagram will change. That they have also looked into. So there's a lot of changes now in this phase diagram. Particularly with oxygen vacancies, it turns out the vacancies are not supporting anti-side disorders in many cases. This is something we did when Arjun Joshua's paper came up. And what he showed is that there is a Lifshitz point. I mean, in band structure, you are expecting a Lifshitz transition, Lifshitz point here from band structure calculations. And let me see if I have his data. I don't have time, so I'll just, okay. So this is his curve, experimental curve. So you have the N number density versus the gate voltage, and at around this gate voltage and at a critical density of about 1.68 into 10 to the power 13 per centimeter square, you do find a change in your N versus Vg curve. This is the expected curve if you just assume there is only one band, and the curve actually deviates strongly from this. But this number cannot be pinned very accurately from such a, I mean, this is almost an approximate way of looking at it. So you have a behavior that you approximate for this, and then you see that the expected behavior is not obeyed, and there is a deviation. So this region is fairly large. So what we did is that we actually took now a multi-band situation, multi-band superconductivity in 3. Now you have to go to all 3 bands, and 3 means 6 here because of spin orbit coupling. And then we did a multi-band calculation, including all inter-band superconductivities. So all this, so let me just skip this. And this is this is something interesting. We actually took care of phases also. and we found that the phase actually dies faster if you have if you include the phase in a multi-component superconductor, and the gap actually or the order parameter still survives. So this is the picture. There are these surviving patches of order parameter, whereas the phase has already died down. Phase correlation has died down. This was actually seen long back in a paper in Nature by Avishai, Meyer and company, and interestingly we find the same behavior here. They did it for a different context, for high DC. These are the mid-gap states that you expect in such a situation. So now coming back here, so what we did is that we took this 3-band model, put all the superconductivities and everything in it, and then we tried to look for the signatures of this Lifshitz transition in physical quantities. I'm running out of time. My chairman told me that 10 minutes are reserved for discussion. Okay, so let me just quickly go through. So this is where you expect the Lifshitz point to appear, and what Arghya and company found was that the TC is maximum at that point, superconducting TC. So what we did is that we actually did incorporate. By this time, lots of people started saying that there is correlation because you are dealing with the TI 3D band, so you better be careful about correlations. So we just included correlation in this, and so we did a DMFT plus LDA calculation and took these 3 bands, and these are the values we took from band structure calculations, and the value of U we took to be half the bandwidth, except that one referee insisted that there is a paper by Imada who claims that it's in the very strong coupling regime. It's the only paper we found, but the referee pointed out that paper, and he or she wanted us to repeat the whole calculation at that high strength of U, which is about 2 times the bandwidth. So we did it. So, but anyway, that's the, but I will stick to this low U calculations, which is half the bandwidth, this one, and the U alpha betas are 1/5 of that. Okay, so this is the way the non-interacting Fermi surface looks like as a function of chemical potential, and then you put U in, and then you see that it's a huge change in the Fermi surface topology. So what does that do? It actually, you can see that at the gamma point, your intensity reduces dramatically if you have interactions, and that is going to affect your transport. And so we looked at the transport, and so these are the DMFT Fermi surfaces, and then we use these this theory to calculate the transport, and what we find is the Seebeck coefficient is the one which reveals this transition most dramatically. There are very sharp peaks at each LT transition. We have now 2 Lifshitz transitions. These are these 2. One is going from here to here, and another is going from here to here. So these 2 transitions are manifested in this Seebeck coefficient much better than in these numbers, and then in the Hall data or their NC versus this expected behavior, deviation from expected behavior. So here we could pin down the critical N values much better. The other advantage is that if you can somehow, by putting pressure or somehow, compress by tensile strength, you can reduce the bandwidth, then what will happen is that the critical value will be transferred towards lower NCs. You don't have to go to such high gate voltages to produce the Lifshitz transition. So this is how DC conductivity behaves. There's a huge pileup of densities here, and that reflects in this. The other interesting thing is that you can actually produce multiple Lifshitz transitions in this, which has not yet been seen, and it's our prediction that you can put a magnetic field and then you separate these almost degenerate 3 orbitals into well separated 6 orbitals except at gamma point, and then you will see multiple Lifshitz transitions, which is as a function of magnetic field, and then these numbers, the critical values of densities at which these occur will be very different, and you can actually see all three in one set of experiment. So this has not yet been done. Okay, so we did many more things, but I think I will leave it at this. Thank you so much.